Hello, this is Neil Hansen. I'm a diagnostic radiologist in Omaha, Nebraska, bringing you Lecture 2 in our physics series, Interactions of Radiation and Tissue. I do offer questions within all of my lectures for kind of practice as well as keeping you awake and engaged. If you're doing at least a click here or there, you won't fall asleep nearly as easily. So if it's live, feel free to go to Poll Everywhere, Neil Hansen 357. If we are not live, which obviously on this YouTube video we are not, then feel free to go to the link within the descriptor here on YouTube for a Poll Everywhere online quiz. We are covering RSNA module number 2, Interactions of Radiation and Tissue. Here are some selected references which you can utilize also. The goals here are just to briefly review anatomic structure, to talk about photon tissue interactions, including coherent Compton scatter and photoelectric absorption, to talk about charged particle interactions, and to talk about photon attenuation and its effects on medical imaging. Here is the Poll Everywhere link, which is also available in the YouTube description to do the questions that accompany this talk. So, photon interactions. What is a photon? A photon is just an energy packet with no mass or charge. The most common examples in medical imaging would be an X-ray or a gamma ray. Photons are used in imaging predominantly interact via three mechanisms. One, they can interact with matter by doing coherent scatter. They can also undergo something called Compton scatter or undergo photoelectric absorption. So let's talk about interaction number 1, which is coherent scattering. This is where a photon enters a target, kind of oscillates and jiggles around, and leaves at the same energy but in a different direction. There is no ionization that occurs during coherent scattering, and it's more likely to occur at photon energies. So you have an incident X-ray coming into this atom. It just kind of jiggles around and changes direction, but doesn't lose any energy. That is coherent scatter. So when a 30 keV photon is coherently scattered, what is the maximum energy loss? This is a literally like 30-second short-term memory test. Pause now if you need more time. Correct answer is 0, right? 0 kVs, kilovolts, because in coherent scattering, there is no energy loss. Photon interaction number 2, Compton scatter. So what happens during Compton scattering? It's where the photon hits an outer shell loosely bound electron. The electron may leave, absorbing some of the energy from that photon. And if the photon leaves, or when the photon leaves, it's in a different direction and with less energy. Some of the energy has been imparted into that electron, which absorbed it from the photon. So the photon is going to leave with subsequently less energy. Randomly, this occurs and it results in backscatter. So when we talk about the useless radiation that's generated like in a fluoroscopic room, that's causing a lot of backscatter, not contributing to the medical image, just contributing to like the dose to the lens of the operator's eye, we're talking usually about Compton scatter. So Compton scatter, photon comes in, imparts some energy onto an electron in the outer orbiting shell, and then leaves in a different direction with less energy. Compton interactions dominate for photons used in imaging with energies more than 25 to 30 keV. This scatter just damages image quality at high levels, and that's why we have to do a whole bunch of things when we do radiography, like use a grid or use an air gap, which will be discussed in future lectures to try and eliminate these Compton interactions from just degrading the medical image. Here's an example of a grid. If you don't know what I mean by a grid, it's where it has these intervening septa that have material which allows the photons or X-rays through, and lead strips which obviously absorb preferentially the scattered X-rays to eliminate all of that Compton scatter, which is just degrading the images. Photon interaction number 3 is photoelectric absorption. This is where essentially all of the entering photon energy is imparted on those tightly bound inner shell electrons, and those inner shell electrons are then ejected. So that photon energy by definition has to be greater than the K-shell binding energy, keeping that electron in that tight inner electron shell orbit. It results in a characteristic X-ray emitted, as you remember from the last lecture, where one of those orbital, more peripherally orbiting electrons, when it falls down from the outer shell to the inner shell, a lot of times the excess energy that's created is emitted in the form of a characteristic X-ray. That can be absorbed by local tissue. So here's an example of that happening. Incident electron here is kind of scattered out via photoelectric absorption, where that incident photon has sufficient energy to knock out that electron. Then a higher order electron falls into that inner electron orbit. A high energy secondary electron can eventually go down to the inner electron shell by releasing a characteristic X-ray or an Auger electron. So again, you have an incident photon. It can knock an inner shell electron all the way out of the inner shell orbit. Then one of the higher energy secondary electrons falls back or falls down into the orbit, inner electron shell, or by definition the K shell. And then a characteristic X-ray can be released. The key here is that there's a sharp increase in the photoelectric effect at energies that are just above the K-shell binding energy. So at diagnostic X-ray energies, the K-shell binding energies of iodine, which is 33 keV, and barium, which is 37 keV, happen to be particularly useful. That's why we use iodine and barium in contrast agents, because that photoelectric effect is common at the energies that we use to expose people to in CT or radiography. So that photoelectric effect inherently creates contrast between the iodine and barium administered and the surrounding soft tissues of which they're located. So to graph that out, if you look at energy or kiloelectron volts, keV, on the x-axis here, and then how much of the absorption is occurring within the tissue, the higher energy electrons, they're not getting absorbed, they're higher energy, there's more scatter. So the higher the energy, the more things that are degrading the image, kind of Compton coherent scatter going on. And then boom, once you hit that K edge of iodine or barium, a significant amount of absorption occurs right at that K edge of the given materials, and significantly more of them undergo photoelectric absorption then, rather than just being lost as coherent scatter. So what energy has the highest chance of photoelectric absorption by an atom of iodine, which has a Z of 53? Pause now if you need more time. The correct answer is 35 kiloelectron volts. So iodine, again, if you go back here, the K edge of iodine is around 33. 33 here, barium is 37. Don't be fooled by the Z number being 53. I put that in there as a distractor. Just above the K edge, 33 would be 35, so A is the most correct answer. A key concept here is that the photoelectric absorption that occurs is proportional to the atomic number cubed. So it's a very, very exponential process. It's inversely proportional to the photon energy cubed. So additionally, like exponential process. So as a result, a small difference in atomic number, like calcium versus soft tissue in mammography, can result in a significant difference in photoelectric photon absorption. And this inherently creates tissue contrast, because the differing number of photons or X-rays that are absorbed create the contrast that our eyes see in the eventual picture. This is essentially an all or none phenomenon with the photoelectric effect, which creates inherent tissue contrast. If you look here at the atomic number or effective atomic number for these given elements and materials, you can see that there are some things like fat, water, and muscle that are very close together. So we have to manipulate the X-ray machine and the detector to maximize out the photoelectric effect to try and tease out the differences in those materials. It's relatively easy to differentiate bone, which has an effective atomic number of 12, from water, which is 7.5, but telling the difference between water, fat, soft tissue, cancer is much more difficult, and hence we have to really utilize both iatrogenic or given contrast like in iodine and lead, as well as the photoelectric effect. Here's the atomic number graphed out in relation to the binding energy. So if you see like iodine at 53, and their electron energy around 30, it just kind of graphs it out. And you can see there's a sweet spot of increased photoelectric interactions between 30 and 70 keVs, which is, again, why we commonly use this energy level for diagnostic imaging. All are examples of interactions between X-rays and matter, except which of the following? Pause now if you need more time. The correct answer here is Bremsstrahlung. Bremsstrahlung, which is our next topic. So Bremsstrahlung is an interaction between a charged particle and matter. All the others are interactions of photons and matter. So a photon has no mass. A charged particle obviously would have mass. Photons are just basically energy. So charged particle interactions is the next topic of discussion. Charged particles, like an alpha particle, beta electrons, beta plus positrons, transfer their energy by either excitation, ionization, and radiative loss, or Bremsstrahlung. So it's important that you don't misinterpret coherent scatter, Compton scatter, and the photoelectric effect, which are all photon interactions, which excitation, ionization, and radiative loss, which are charged particle interactions. Sometimes charged particle interactions will result in photon generation, which makes it kind of confusing, but it's important to keep them distinct and separate. So, excitation and ionization, why is that important? Well, ionizing radiation causes cancer, so that's really kind of a big deal. So it's important to know about it. And excitation and ionization are where the interactions occur between charged particles that involve the target shell's electrons. Bremsstrahlung, on the other hand, is an interaction with the target's nucleus. All right, excitation. So excitation happens when an energy is imparted on an atom, but it is not enough to knock out the electron from its inner shell. The partially excited electron de-excites and emits electromagnetic radiation, usually in the form of heat. So there's some sort of charged particle interaction. An electron gets excited, but it stays within its shell. It's not so much that it gets released away from the atom, and it falls back to kind of baseline and releases radiation, which is usually infrared in the form of heat. Is it hot in here? Oh wait, it's just me. Charged particle interaction number 2, ionization. So ionization occurs when the incident energy is sufficient to knock an electron out of the atom, and it forms an ion pair. So you have a charged particle, comes in, interacts with an atom, knocks one of the, or sometimes more than one, electron out of that atom, and creates a ion pair or a charged particle pair. Charged particles like positrons, electrons are directly ionizing. So this, as you could imagine, creates a cascade, where once you've created one, that one goes out and creates others, which then go out and create others, creating a downstream effect of ionization events. Other radiation forms, like photon interactions, are indirectly ionizing. So photon interactions like Compton scatter, coherent scatter, photoelectric absorption, technically those are not ionizing interactions. However, they do lead to products which then become ionizing in and of themselves through charged particle interactions. Here's an example or a graphical representation of the various forms of radiation energy. You have low energy, non-harmful waves like radio waves. You have microwaves. Then you get up into the things that can do soft tissue damage and harm. So like infrared, below red, obviously here's the visible light spectrum. Infrared, red, orange, yellow, green, blue, violet. And then you start to get to the things that really cause tissue damage. So ultraviolet light obviously can cause skin cancer. Conventional radiography, if you just radiated the crap out of somebody, you could turn them red and give them a burn. Then you get up to the things that really cause burns and can even cause, lethal soft tissue damage, like radiation therapy levels of radiative energy. So why is ionization important to us? Why are these charged particle interactions important? Well, they cause cancer. Also, they can cause skin burns. So this was a patient that underwent a heart cath, and the X-rays generated during that heart cath were detrimental to the skin. Obviously, caused a pretty bad skin burn. Most modern fluoroscopic equipment and cath machines have controls which prevent this from happening. They'll give you warnings and alarms, but it's still not unheard of, even with modern technology in place, for radiation, especially during very lengthy fluoroscopic procedures, to get a very high skin dose and potentially skin erythema and burns. All right, just like the Fukushima leader here, the radiation is under control. All right, which of the following matches common anode materials with their common characteristic X-ray energies? I'll give you a second, or you can pause if you need more time. The correct answer is tungsten 59, molybdenum 17.5, and rhodium 20.2. Tungsten is the most commonly used atom in an X-ray tube generating machine. Molybdenum and rhodium are used in mammographic imaging setups because of their preferential causation of the photoelectric effect, which we'll kind of get into. All right, X-ray production from ion interactions. Depending on the particular orbital shell involved, any given atom can release one or more types of characteristic X-rays. These are polyenergetic. Probably the most common thing that happens during these ion interactions is that a wide spectrum X-rays is released, all the way from kind of coherent and Compton scatter junk, which is kind of lower energy photons generated, to characteristic X-rays related to the photoelectric effect. So each atom releases a variety of characteristic X-rays along a spectrum. So if you look at the photon energy here and the relative intensity of the X-rays made, there's all sorts of Bremsstrahlung interactions which lead to this low energy crap. This stuff kind of only degrades imaging. It's not really used per se. It causes background noise in the images, and there's lots of filtration devices that we use to get rid of these because they only really contribute to skin dose. Then you have your characteristic radiation that's emitted at those key energies, for the given tissues being irradiated, and then it goes all the way up to the high energy photons to the maximum of what you're using for your X-ray generation setup, which is artificially picked. If you set the CT scanner for 120 kVp, the maximum energy that's going to come out of that is 120 kVp. The average may be something like 70. All right, to go a little bit more in depth on Bremsstrahlung, or charged particle interactions. Rather than interact with an electron, Bremsstrahlung occurs when a particle interacts with the nucleus of an atom. So a charged particle will go interact with the nucleus of an atom, and what happens is it changes course and slows down. Bremsstrahlung is the German word for braking. So as that charged particle goes in, doesn't interact with electrons, instead it interacts with the nucleus, it changes direction and slows down or brakes. That energy is converted into a polyenergetic X-ray spectrum from 0 to whatever your max for your setup is, which again in diagnostic imaging will set that. That's one of the set parameters, for example like 80 kV or something like that. And in addition to the polyenergetic X-ray spectrum which is produced from these Bremsstrahlung interactions, there's also a fair amount of heat. This is why those anode materials get very hot when we get to the point of talking about X-ray generation. Do we use Bremsstrahlung? Well, kind of rarely we'll use it in medical imaging. For example, after Y90 treatment, Y90, which undergoes beta minus decay, and Y90 is usually used for treatment of hepatocellular carcinoma and interventional radiology. You can use Bremsstrahlung radiation to image where the radiotracer dose was delivered. So this is usually delivered intra-arterially via a catheterization. And you can do Bremsstrahlung imaging afterwards with a nuclear medicine camera to ensure that the radiopharmaceutical was delivered to the correct segment to the tumor. All right, now we're going to talk a little bit about the specifics of an X-ray tube and how it interacts. There are two basic parts of an X-ray setup, a cathode and an anode. The cathode is a heated filament which essentially boils off electrons after being exposed to an X-ray source. So I'd like to think of it as kind of just like plugging it into the wall. It's a little more sophisticated than that because it takes a lot of energy to run one of these radiographic units. But essentially an electricity source is hooked up to the cathode, a filament is heated, and it boils off electrons. An applied voltage across the cathode to the anode directs those electrons so they're not just scattered all about, and it focuses them towards the anode target. Then those magical charge particle interactions occur. I'm going to show you a YouTube video, and I can appreciate the irony of showing you a YouTube video within a YouTube video, but there are several great YouTube videos on physics, and mine is merely a small shell of probably what you should be using to learn physics. But I'm going to bring it up here and let you watch this real quick so that you can learn about these interactions.
Production of X-rays. The lab setup shown here was designed by Coolidge, and hence it is called Coolidge Tube. It contains a highly evacuated glass bulb containing a cathode, which is a tungsten filament, and anode, which is a target made up of metal of high atomic weight. The pressure inside the bulb is maintained at 10 to the power of -6 millimeters mercury. When the cathode is heated by passing a current through it from a low-tension battery, it emits cathode rays. These rays are nothing but electrons. The filament is surrounded by a molybdenum cylinder, which is kept at a negative potential to the filament. This repels the electrons further, and hence the electrons form a fine pencil beam at the center of the cylinder. This pencil beam is also accelerated by the cylinder towards the target. The target is made up of a copper block in which a piece of tungsten or molybdenum is fixed. High thermal conductivity is used to carry away the heat generated to the cooling setup. Here we use copper, which is a good conductor of heat and can take the heat away from the molybdenum metal towards the water cooling system. The target is also tilted at an angle of 45 degrees, causing the electrons to hit at an angle. This will produce the X-rays almost perpendicular to the electron beam. A very high potential of 20 kV is applied between the source and the target. Due to the high potential difference, the electrons are accelerated towards the anode and it hits the metal. When it hits, the kinetic energy is transferred to produce X-rays. The intensity of the X-rays depends on the number of electrons striking the metal target. So, if we can increase the rate of electrons emitted by the filament by increasing the current flowing through the filament, then we can increase the intensity of the X-rays.
Obviously, the
X-rays.
Obviously, the X-ray tubes that have been created are much more sophisticated than those Coolidge tubes, which were, very early in radiology's infancy. The tubes nowadays, they have different materials that are better at generating X-rays and or better at absorbing heat. They have anodes, which are very complex that spin around to dissipate heat. But that was a very basic setup. So for radiography, fluoroscopy, and CT, usually the anode target is tungsten. For tungsten, the primary interaction is actually excitation, which makes it very, very hot, and that heat needs to be dissipated. Bremsstrahlung interactions account for most of the X-rays that are generated, and those are of a widely varied spectrum. If you remember before about Bremsstrahlung, it just creates, kind of a bunch of crap X-rays from 0 up to the kVp or the K max. The voltage applied between the cathode and anode is what determines what the maximum photon energy coming out of that spectrum is going to be. Ionization leads to characteristic X-rays only for about 0.1 to 0.15% of overall interactions involved in most of these anode interactions, so it's a very inefficient process overall. All right, how hot can the tungsten target get in a CT tube, typically when we're doing a CT scan? Pause now if you need more time. The correct answer is 4,500 degrees Fahrenheit. All right, mammography always deserves a little bit of a special attention because it's a little bit different than your typical CT or radiographic setup. The anode targets are typically made of rhodium or molybdenum. That's because they have much lower K-shell binding energies. It results in characteristic X-rays that are typically 18 to 22 keV. There is much less Bremsstrahlung interaction, which leads to a much tighter tube spectra composed mostly of characteristic X-rays. If you look at the X-ray spectra, and I have a couple examples coming up of the X-rays coming out of a mammography setup, it's a much cleaner graph than that associated with tungsten. So again, the basic setup is the same. Heated filament, gets heated up, thermionic emission, electrons which are focused towards the anode material, and the anode material, which happens to usually be rhodium or molybdenum, those interactions occur, which eventually lead to characteristic X-rays being produced and focused towards the thing being imaged, in this case, a breast, usually looking for cancer. Here's the X-ray spectra. So you can see there's a lot more in terms of characteristic X-ray production and a lot less of the low energy kind of junk created through Bremsstrahlung interactions. Now we have more boring nomenclature measurement stuff. All right, secondary ionization. So I talked a little bit earlier about how ionization, once you create an ionizing particle, it tends to ionize other things and leads to a cascade. That's where this comes into play. So the electron ion that's originally released during an ionization event can and will go on to cause additional ionization events within the same atom or in nearby atoms. The chance of this decreases the farther away you get from the primary event because a lot of that energy gets absorbed by the material it's going through. But it occurs, and it can occur to variable depths depending on how strong the initial events of ionization were. There's another concept called specific ionization. If you think about it, charged particles give up energy continuously along their path. So it's not like it's a one and done. It can be, but usually it's not. It's usually a charged particle that's giving up energy in a continuous fashion. And specific ionization just describes how many ion pairs are formed from a primary and secondary interaction per distance traveled. So how many ion pairs per millimeter. So specific ionization is directly proportional to the charge of the particle, but indirectly proportional to the velocity. And that makes sense, right? So if a particle is charging very fast, your relationship to the specific ionization is going to be inverse because it's going to be able to travel a farther distance before giving up all of its energy. The Bragg peak kind of graphically illustrates this point. As a particle goes through tissue, it loses its velocity and its kinetic energy. That loss of velocity increases the chance of an ionization event. So when you lose velocity, you're hanging around more in a local environment, and the chance of an ionization interaction occurring goes up. If you plot those ionization events versus distance results in that Bragg ionization peak, that's where the maximal number of ionizations are going to occur. So if you are going along depth of penetration, all of a sudden that particle hits this magic Bragg peak where it's slowed down enough to interact, and a bunch of interactions, ionization interactions occur to the point of where they kind of burn themselves out. All right, and energy is typically used in diagnostic radiology. Where does the Bragg peak occur? Go ahead and pause now if you need more time. The correct answer is skin entry site. That's why skin dose is so important, because many of those ionizing interactions occur within the first 2 to 3 centimeters of the skin. I usually give this talk around the time of the Super Bowl, although who knows when you'll be watching it now. But I do like to include some Super Bowl facts just to keep people awake and interested. There's usually close to 500,000 halftime tweets. 325 million gallons of beer are drunk during the Super Bowl. 13.5 million Puppy Bowl viewers on average every year. If you're not a football fan, check out the Puppy Bowl. 48 million takeout orders. That's more than the population of Canada. So take that, Canada. If we have any Mounties that are watching this. 12.5 million pizzas are eaten. There's a 15% rise in DWI, driving while intoxicated. So please be responsible as you go to and from your Super Bowl parties, if we can even have them with the pandemic this year. There's a 10.8% surge in porn consumption based off of Denver Broncos loss in 2014. So I guess people are, there's no football. What am I going to do with the rest of my day? I like these memes. I ate so much, Weight Watchers going to sign me. The Super Bowl this year will probably be no fun as usual. I've gained a little bit of weight, put on my COVID-19 pounds, that is. So, I'm going to be doing a lot of carb cycling, and I do a low-carb diet. I can lose a lot of weight real quick, and, my attitude goes south. So maybe serial killers are just normal people on really low-carb diets. What? Eating fat equals weight loss? That one kind of blew my mind as well when I first learned about that. Eat bacon for breakfast, no one bats an eye, but eat beef jerky for breakfast, and everyone loses their mind. My wife put this up in the bathroom at our house. Every time you eat bread, Ryan is sad. What if I told you there are low-carb recipes for pizza, bread, and even pancakes? I would tell you that they all suck, which is kind of where I'm at right now. Low-carb day. It sucks to be the resident working with me in the afternoon if I'm intermittent fasting or haven't eaten a carb that day. All right, back to boring physics. Line energy transfer. So LET, it's the path of particles relating to their mass. So LET, heavy particles tend to go in a straight line. They're relatively uninfluenced by local charge, or the fancy physics words for charge is Coulomb interactions, whereas lighter particles are more heavily influenced by charge interactions and can be repelled by those like charges or attracted towards opposite charges, and they tend to bounce around and travel indirectly. So if you think about it, heavy particles travel in a straight line. Lighter particles, more influenced by charge interactions, and get repelled and attracted all over the place. This was a Super Bowl commercial from a couple years ago. If you've never seen it, Google it. It's pretty awesome. All right, line energy transfer. So the energy deposited per unit path length traveled. So it's just energy divided by distance. High LET particles have lots of energy delivered in a small space. Low LET particles have energy sparsely distributed, and LET is proportional to charge, inversely proportional to velocity. Again, like the more charge there is, the higher the line energy transfer. The faster it is, though, the less LET it's going to be, because it's going to be moving around and not depositing in one place as much. So how does LET of an alpha particle compare to a particle typically encountered in diagnostic imaging? So the correct answer is it's about 100 times more. So if you look at the line energy transfer of a alpha particle, it has a lot of local damage capabilities. So that's why like radium-223 is effective, right? It lands where a metastatic tumor cell is in the bone and it destroys it. Versus the electrons, beta particles, beta minus particles created during like X-ray imaging, they have a really low LET, which means they're really not damaging typically in terms of immediate radiobiologic effects. All right, alpha damage. So polonium-210 is an alpha emitter. It was used to kill a Russian spy, Alexander Litvinenko, in 2006. He was a KGB defector turned British informant. 50 millicuries of polonium-210 was all that was needed. Alpha emitters are very difficult to detect, and this guy went from this to this in a very short time because the alpha emitters just do so much local tissue damage. Interestingly, polonium is also what Tony Stark has in his chest. For the Iron Man fans out there, at every opportunity I try and get an Avengers reference into my lectures. All right, the last concept is photon attenuation. So what is attenuation? It's the removal of photons as they pass through a substance. It's the result of scatter and absorption. It's a result of an exponential decrease per unit distance traveled. Low energy photons, attenuation is primarily via photoelectric absorption. High energy photons, predominantly Compton scatter. How is all this relevant to the images that we acquire in diagnostic radiology? Well, the differences in tissues in the body result in different ways that X-rays or gamma rays are absorbed. So if you have different tissues, they're going to have different atomic numbers, even if it's subtle, like between, the liver and kidney, which are both soft tissue. They still will have slightly different atomic makeups and slightly different atomic numbers. So they'll absorb different amounts of the X-rays they're exposed to, and that will induce contrast in the images, which allow our eyes to tell them apart. If you think about the chest, like you have bone, ribs, and lung, which is mostly air. So those tissues really have a high differential absorption of X-rays in and of themselves. So the setup is going to be different than if you're imaging a breast for cancer, which has relatively low differentials in absorption. Fat, fibroglandular tissue, and cancer all really are very close in atomic number and density versus like bone and air are not. And then again, we can administer things like iodine and barium, which will artificially give us a higher differential absorption rate and be able to evaluate things like vasculature, the GI tract better. So again, inherent tissue differences, like in a chest radiograph, will require a much different setup than things like the breast, which have a much higher need for differential tissue absorption because everything is pretty close to the same. So a little bit about photoelectric absorption. This contributes to patient dose, obviously, and is more likely to occur in the skin with lower energy photons, which isn't a big deal if you're imaging thin structures. So if you think about a mammogram where the breast tissue is compressed to be as thin and still as possible, the patient dose issue isn't as big a deal. Metal filters are used in X-ray tubes. So if you're doing like a CT scan of the abdomen, you're going to use a metal filter to absorb those lower energy photons. You wouldn't use that same setup in a mammogram because those low energy photons are giving you the photoelectric effect, which is kind of what you're using to differentiate tissues, which is a whole different setup in CT. But in CT, to avoid that high skin dose, you'll use metal filters to absorb some of those low energy photons and help mitigate the photoelectric effect in the skin. Again, I just want you to take you back as we get into the nuts and bolts that the process is going to be the same regardless of a CT, radiographic machine, mammography setup. You got a cathode filament, heat it up, move an electron across a potential, hit a tungsten target or a molybdenum or rhodium target. Usually these are on a rotor and a spinning anode. That's just used to dissipate heat, to spread out the thermionic emission target space, so to speak. So you're not hitting one focal point, you're kind of spreading it around the anode material. Then as the X-rays that are generated come out, especially on CT scanners, you'll have something like aluminum or sometimes copper filtration. Then you also have collimators to prevent backscatter in the room. So while lower KEVs allow for better tissue contrast, like in mammography, in thicker parts of the body, like my belly, my abdomen, soft tissue absorption of these low KEV photons really would prohibit their use. To get a diagnostic image, so much is getting absorbed by my abdominal fat, or rather my giant ab muscles, that you'd have a skin burn, so you can't use them. So for thicker, more dense parts, you have to use a higher average kVp. Like in the breast, you'd use 25 to 30. In a hand, you use maybe 50 to 55 because you have bones there that are denser. And in the abdomen, because you have so much soft tissue and absorption to get adequate penetration through with the amount of radiation you're using without causing a skin burn, you have to use higher energies, like in the 70 to 90 range. More nomenclature. The linear attenuation coefficient, otherwise known as the Greek symbol mu. The fraction of incident photons attenuated per unit thickness of material. So this is proportional to density, and it's kind of intuitive to think about it. So if you have a linear attenuation coefficient that is high, so like if you take iron, for example, iron is very dense, has a very high linear attenuation coefficient. It's going to attenuate a lot or absorb a lot of the incident photons per unit of thickness. X-rays are not going to move through that very efficiently. If you look at like lead, why do we use lead for shielding? Well, because gold is too expensive. You can't have a platinum gown, but no. So lead has a very high linear attenuation coefficient. It prevents, it rather absorbs so much of those incident photons per thickness of material that it prevents a lot of that exposure to our bodies. Versus if you think of like air has a very, very low linear attenuation coefficient because it's not absorbing and attenuating much as the photon travels through it. The mass attenuation coefficient is another unit that you have to be familiar with. Since the linear attenuation coefficient is dependent on density, the mass attenuation coefficient corrects for this by normalizing to a standard unit of density and puts it in units of centimeters squared per gram. So it basically takes as the linear attenuation coefficient and standardizes everything for a given density, which inherently different materials have different densities, which factors into that even irrespective of their individual molecular properties, which cause them to attenuate the incident photon beam differently. All right. These two graphical representations kind of illustrate some of the effects that we just kind of learned about their nomenclature. So if you look at the maximum or the mass attenuation coefficient for soft tissue and what photon interaction dominates, you can see here that at these really low energies, you have things like the photoelectric effect. So at these lower energies, you have the photoelectric effect. Again, mammography, lower energy, burning that into your brain, which becomes less and less relevant as you get to these higher energies above the photoelectric effect threshold of the given soft tissue, versus the coherent and Compton effects, which tend to remain even at these higher energies. And really at the very high energies, like once you get above 50 to 60 keV, it's mostly Compton scatter. So if we're doing a maximum kVp of 120, for example, for a CT scan, the dominant interaction in the room is going to be Compton scatter from those higher energy photons. If you look at different materials and how they attenuate the X-ray beam, at any given energy, bone is going to attenuate more of the incident X-rays than soft tissue, right? It's more dense, has a higher linear attenuation coefficient, so at any given energy it's going to attenuate more, but the effect is much more pronounced at these lower energies. So it's much more pronounced from the 0 to 50 range than 50 to 100, and once you get above 100 keVs, it really doesn't matter the difference between bone and soft tissue. The photons are so energetic, they're really not going to be attenuated much at all. So above these energies, it's kind of pointless to use these energies for many diagnostic imaging applications because they're all just going to go straight through without getting attenuated. And without differences in attenuation, we don't have an X-ray or a CT. All right, the concept to go over next is the half value layer. So the half value layer is the thickness of material, often in reference to aluminum as a standard, that's required to reduce the intensity of an X-ray beam to half its original intensity. So it's just how thick something has to be to get an X-ray beam down to half. This measures the penetrating qualities of a given beam. For most plain films, the half value layer of the X-ray tube used is about 3 to 4 centimeters. So by the time, if you're getting an abdomen X-ray, by the time the beam has gone through 4 centimeters of soft tissue, it's already down to half its original strength. In mammography, the half value layer tends to be smaller because you're using lower photon energies, so it has a half value layer of about 1 centimeter due to that lower energy beam. If you look at the half value layer for like a diagnostic X-ray tube, 80 kVp, about 3.5 millimeters, if it's going through an aluminum attenuator. So, you're limited on how much aluminum you can use for filtration, because if you use 10 half value layers, you're going to cut it in half and half and half and half, and you're not going to have any beam left. In soft tissue, it's about 3 to 4 centimeters, like we said before. For mammography, they require a lot less filtration, if any filtration is used at all in the setup. Because of the lower energy photons, the half value layer is a lot less. Same thing in soft tissue, half value layer is a lot less. If you talk about technetium and gamma rays produced, they're at 140 keV. And remember, the higher up you go, the more difficult it is to attenuate that beam. So really, you'd need thicker lead to attenuate that beam, and those higher energy photons are going to go through more soft tissue before you're down to half. So a higher half value layer. All right, the soft tissue thickness that is most likely to attenuate an 80 kilovolt X-ray beam by 50% is which of the following? I'll pause here and give you a chance to answer. The correct answer is 3 centimeters. You don't have to do any math. You just have to know that soft tissue, if you use an average beam in radiology, which is an average beam is going to be somewhere close to 70 or 80 kilovolts, that the half value layer is usually in the skin, 3 to 4 centimeters deep to the skin surface. All right. You can also calculate the half value layer if you happen to know the linear attenuation coefficient for a material. You just take 0.693 divided by that LAC. All right, nomenclature. The last little bit of nomenclature I promise for today. The 10th value layer is how thick something has to be to reduce a beam intensity to 1/10 the original strength. Often this is used for designating appropriate levels of lead shielding in rooms. If you think about designing a room, there are federal regulations for how much radiation the public or a healthcare worker can be exposed. So when we design an X-ray room, we have to make sure that the lead lining of the walls is going to make sure it's thick enough to make it a 10th value layer or something like that to meet federal guidelines, so that we're not exposing people in the hallway or administrative staff that aren't wearing lead to inappropriately high levels of X-ray beams. The concept to kind of finish on is beam hardening. This occurs when the lower energy photons in a polyenergetic beam are preferentially attenuated by dense material. On CT, this can result in streak artifact. If you think about it, as X-rays go through tissue and tissue and tissue, if you look at the X-ray spectra produced, here they're full of a bunch of lower energy photons. A pretty significant portion of this spectrum is low energy, but all of those are absorbed during this 10 centimeter tissue, traveling when it travels through it. And you have a functionally harder beam with more higher energy photons. If you do that again, it's going to become even worse. More of the lower energy photon are eliminated, and you have a harder beam that's more penetrating with higher average photon energies. And if you do that over and over and over again, or if you just do it through something that's incredibly thick or dense or has a high linear attenuation coefficient, you're going to get a functionally very hard beam, which is full of higher energy photons. And if you do that to maximum, like here in the posterior fossa, or in something like that's metallic or very, very dense, is going to create this artifact on CT called beam hardening artifact. Adding a filter. So if you added a filter, which would be unlikely to increase? The correct answer is air kerma. If you think through it, if you add a filter, you're going to remove lower energy photons, and that's actually going to increase the beam penetrating power. It's also going to increase the average beam energy, and it's going to increase the half value layer of the material that you're going to use to have to try and prevent it from going through. The only thing it won't increase is air kerma. So air kerma is just a fancy way of saying the overall amount of radiation. The overall amount of radiation is going to be less because any filter essentially just removes radiation, preferentially the lower photon energies, but the air kerma will in fact decrease. So adding a filter causes beam hardening, a beam with a higher penetrating power, a higher average energy, and a higher half value layer. The heel effect. So what is the heel effect? The heel effect is caused by X-ray absorption in which of the following? Oh man, I didn't clear out the answers. I'm so embarrassed. Hopefully everyone got this right. The correct answer is anode. All right, anode. There are videos. I'm not going to show it now because I'm running pretty long on the video here today. But if you Google a video on YouTube for heel effect, there's lots of really great descriptors. And I'd say it's critically important to understand the heel effect. It's one way that we can practically question people about physics in terms of it alters the way we set up the X-ray beam and the patient positioning and create artifacts. So it's ripe for asking a question around. So in terms of fundamental concepts, I'd say you have to know about the heel effect. What it is that the intensity of radiation is greater on the cathode side of the tube, this side over here, because there's absorption within the anode due to this angulation which directs the X-ray beam towards the person. So to ensure an even image density, the cathode is typically placed over the thicker part of the body. So if you think about it, on this side, because there's more anode material, you're going to have a relatively less intense beam because some of the beam is absorbed within the anode itself. On the side near the cathode, you're going to have a more intense beam because there's less traveling through the anode, functionally resulting in a higher intensity beam on the cathode side. So what you can do is if you put the cathode over the hip here, you have a nice uniform image. The hip is thicker than the knee. So the cathode has a higher intensity beam over the thicker part, creates a more uniform appearance. If you put the cathode over the knee, you get over penetration here. You can't even see the soft tissues here because they're completely bleeded out through the over penetrating higher intensity cathode part of the beam, and you have more trouble seeing the thicker parts here because the anode side of the beam is less intense. So we position the patient relative to the cathode and anode with the thicker part being cathode directed. It creates a more uniform, better image with less overall radiation exposure. They like to test this about chest x-rays. So the ideal chest x-ray, on the ideal chest x-ray, you should barely see the vertebral bodies behind the heart. So this is like what a thoracic spine radiograph looks like. You can see the spine almost better than you can see the heart, or at least equally as well. This is bad. This is over-penetrated. And the reason being is that it's the position of the cathode and the anode, right? So if you put the cathode down here, there's functionally more penetration from the higher intensity part of the beam, and you've gone through the heart, and you can see the vertebral bodies more. So just know that is directly related to the anode heel effect. All right, the heel effect. So you can compensate for this by placing the denser portions of the body on the cathode side of the tube and the thinner parts of the body on the anode side. The heel effect is most likely minimized by increasing the following. So here's where I'm really embarrassed because I did pause the video, I cleared out all the answers, and now I just don't know why it's still on there. So I'll do it again. All right, I'm back. So now you don't know the answer, I guess. Honestly, I'll go back and edit this out later. I say that knowing that like this is taking a long time to make these videos, so I'm not going to do that. But I'll just say that the correct answer is the anode angle, the anode angle. So if you look at the anode, and if you have a smaller anode angle, you'll have a narrower useful beam versus a larger anode angle, you'll have a wider, more useful beam. However, the Heal effect will be altered, right? Because functionally you have more distribution of less intense to more intense beam. In order to take advantage of the Heal effect in PHS radiography, the X-ray tube should be oriented which of the following? Pause here if you need more time. But traditionally, for chest radiographs, the X-ray tube should really be oriented with the anode towards the head and the cathode to the feet. It's thicker down by the lower part of the chest than up by the lung apices, and so you can functionally use less radiation by putting the cathode towards the feet. All right, so that ends our show. I really appreciate you putting time into these videos, and hope you have a great day.